Está agora em direto.
Okay, so good afternoon to all of you. I'm very happy to say that we are here to discuss one more PhD thesis. And so today we are going to discuss the thesis of Mohamed Fouad Hassan Lotfi Mahamoud. The thesis is entitled Decentralized Cloud-Based Approaches for Cross-Sector Demand-Side Management. And I have to thank at the beginning first to all the members of the jury for their availability and for having accepted to do this discussion. And of course, I want also to wish good luck to the candidates. And Mohamed, you know the rules, I believe. So you have now 30 minutes for your presentation. Try to keep the time. And then we follow with the discussion. And I also believe that all members of the jury, they know their roles and the times that have been allocated to each one. So let's start. Mohamed, the screen is yours.
Let me share my screen. Can you see my screen now? Yes?
Yes.
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 Okay.
Okay. You can start. Go ahead.
Okay. Just minimize Zoom. Okay. So thank you very much. I will begin by presenting an overview of my PhD thesis.
Mohamed,
Yes.
sorry to interrupt, but you are not in full screen mode. You are sharing the PowerPoint.
Ah, yes, it's the presenter view.
It's a presenter view. It's not on the screen mode, full screen mode. Okay, now it's full screen mode. Okay, please proceed. No, you get back again to the. It was okay, and then you move it again to PowerPoint mode. Now it's okay. So carry on.
You are muted, Mohammed. You are muted.
You are muted, Mohammed. Your micro is closed. Now your micro is on.
Okay. Sorry for the confusion.
Okay.
I will, yeah, sorry for the confusion. Okay. Thank you very much. I would like to start by presenting an overview of my PhD thesis titled Decentralized Cloud-Based Approaches for Cross-Sector Demand-Side Management. It was supervised by Professor João Catalão and also the co-supervision of Professors Claudio Monteiro, Professor Gerardo Zorio, as part of the doctoral program in Sustainable Energy Systems at the Faculty of Engineering of the University of Porto. I would like to thank the funding of my work through the FCP grant, co-financed by Portuguese and European Union funds. During my work, I was hosted at INESC-TEC, the Center of Power and Energy Systems. I also spent 6 months as a visiting scholar at Ontario Tech University in Canada, and my work was involved in 2 research projects, the SGRIDSCOM P2020 project and the United FCP project. So to start with the context and motivation of my work, we don't need to look any further than the global crisis we are facing today, from climate change to overpopulation and the increasing need for energy demand and the spikes in peak demand, and also even humanitarian crisis with developing countries having a dire need for the energy infrastructure and energy resources to industrialize. globally, we tackle these issues by investing more and more in developing rapidly renewables and greener energy resources and technologies such as electric vehicles. But by doing so, we have created another problem of its own. And nothing says this better than the Economist magazine cover of last week. We've created some sort of an energy shock, and the words here are perfect. We have symptoms of dysfunctional global energy markets. We have grave problems with the transition to clean energy power. Many countries have made pledges, net zero pledges, to rapidly install renewables and green power without tackling the fine print of how this transition will work. And this is what's creating this energy shock. And in fact, this is exactly what this thesis is about. We know what we want globally. We know the solution. We want more decentralized, more sustainable power systems. We even have the ideal vision of the Internet of Energy, but we do not know how to transition to this and how do we manage this transition. And this brings me to the thesis contributions. This work builds on the architectures, approaches, and the technologies in the Internet of Energy paradigm to develop disruptive energy management tools that cover the full spectrum of this transition, from grid operation to the energy management tools adaptation for end users from different sectors. And the primary research question is, can fully decentralized distributed data models ensure techno-economic sustainability for electric power systems and end users from different sectors? So my thesis is divided into 4 parts. The first part serves as an introduction to the context. The second and third parts are the core of the thesis with regards to the developed methods. And part 2 focuses on the grid operation. Part 3 focuses on the end user energy management models. And finally, in part 4, we respond to the research questions and we make some recommendations for future work. Let me start by part 1. In chapter 1, I discussed the history of the development of demand-side management strategies. In chapter 2, I discussed the status quo and the transition that's currently occurring. Chapter 1 starts by identifying what demand-side management is, what are the different strategies involved in demand-side management, and then we go to the origins of this transition, going all the way back to the 1970s, where 3 different events, the economic viability of small generation units, the beginning of the awareness on environmental change, and the beginning of concerns on security of supply have emerged. And as such, a major shift in the electricity sector happened through liberalization and the beginning of incorporation of renewable energy sources. And this was the time when the demand side started being considered as active participants. The pioneers of this change were the US, the United Kingdom, and the European Union, the 3 main zones that led this change. And I begin by gathering and compiling the full list of legislation for each of the 3 zones or each of the 3 regions that led to this change, starting from liberalization all the way to modern demand response strategies for the United States, for the United Kingdom, and the European Union. Afterwards, by compiling all this information, I managed to draw a roadmap, 5 stages on how demand response programs, the stages of developing full demand response programs in smart grids. And then I attempt to link the research trends, scientific research trends, with the legislation, and I got very interesting conclusions from this. As we can see, for instance, here on the right, demand response and smart grids are very old concepts. They've been around since the late 80s, early 90s, but without the necessary legislation to enact them, there was basically very little interest in the scientific community on them. And we will come back to this later when we answer the research questions. After that, I draw the full timeline of how this transition occurred, and then we proceed to the status quo, the recent literature, and from there we can see what is happening in modern day power systems. We have an emergence now. We're taking demand side management to the next step, where we have the Internet of Energy is emerging as a result of increased IoT enabling of smart grids, which is basically a fully decentralized network of energy prosumers. In there, demand response continues to be a vital aspect. And this is happening concurrently with a lot of disruptive changes due to the 4th Industrial Revolution. And this is where chapter 1 ends, and we go on to chapter 2. But first, I would like to indicate the scientific outputs of this part. So we have the 2 IEEE conference papers. The first is the MapCon paper, and the second is PowerTech paper for more reference on this information. Now, chapter 2 takes it from there and investigates how the transition is currently occurring into what we envision for the future. And we start by identifying what the fourth industrial revolution is, what are the simultaneous disruptive technologies that are being developed to enable the Internet of Energy. And we identify, well, obviously, the main enabler is the uncontrollable growth of Internet of Things enabling of the energy sector. But that in itself is creating two main problems: data redundancy and data privacy and security issues. With regards to data redundancy, a major solution effort to tackle this is cloud computing. However, privacy and security issues remain a problem, and with the enactment of GDPR and similar legislation, it is no longer only a concern, but actually a legally binding obligation for all sectors that are affected by this to solve. And speaking of these sectors, the energy sector is one of the most affected by this transition. 10% of all IoT endpoints are going to be energy related, at least with the most pessimistic forecasts. And as such, we need to adapt our mindset to this new paradigm. Then I proceed by doing a literature review on the works done on the Internet of Energy. And a major conclusion made here is that this is the consensus in the gathering of all scientific findings, that any technical models and processes developed in this paradigm must have these four design requirements. One, they must be distributed. Two, they must be efficient at data analysis. Three, they must be scalable. And four, they must be user-friendly. And these are the criteria that I use to develop all the models in the later chapters. Then I quickly go through another aspect that is changing energy systems, which is the emergence of decentralized economies and its underlying framework, which is blockchain. And since the invention of blockchain or the introduction of blockchain, it has went a long way from merely being something that enables digital currencies to now something that can be used for fully decentralized smart contracts and even distributed decision making. And it is seen as the solution to the security and data privacy problem, allowing us to know that there is a secure way of transacting information. So we moved from it being used for financial transactions to the concept of transactive information. And we use a lot the word decentralization of power systems, decentralized energy sector. And that's why I end the chapter by listing the different layers at which decentralization can occur. We have the physical decentralization, which is decentralization of generation, for instance. We have decentralization of information systems, which is due to the IoT paradigm and the abundance of data from so many small sources. And finally, the decentralization of energy markets. And it's important to identify these different layers of how power systems are being decentralized. More information about this chapter can be found in two papers, one book chapter that was published, an Elsevier book chapter, and another one found in the IEEE Smart Grid newsletter article that were both published as a result of this chapter. And so the introduction is done. I move on to the main core of the thesis, which is the development of the new models. And part two discusses the transition to cloud-based operation of smart grids. Chapter 3 discusses the current state of smart cities and how we can coordinate contemporary energy management systems to come up with synergistic benefits from this coordination. And then chapters 4 and 5 take this a whole other step further and try to completely dismantle and completely decentralize the way power grids are managed. In chapter 3, I start by listing the elements of what a smart city is in the current context and how electric vehicles can be seen as the main connector between these different elements. And we develop a conceptual model for this by considering two neighborhoods with home energy management systems and the faculty parking lot, actually modeled as FIOP, in fact, with its own energy management system. Both are linked to a power grid, and the electric vehicles provide the link between these different energy management systems. We develop a mixed integer linear programming model for the parking lot energy management systems, and the constraints are shown here. I put all the equations here, and we can go back to them in discussion, not to waste too much time. This is the objective function. So the parking lot energy management system focuses on maximizing the profit, and by increasing the incomes, by selling electricity, whether to the grid or to the EV owners, and minimizing its cost of purchasing electricity. On the other hand, we have the home energy management system. These are the constraints, and the objective function, of course, is to minimize the electricity bill for the owners. The energy management systems communicate by sharing the expected arrival and departure times. This is how electric vehicles provide this link in a smart city concept. And then we simulate a real case study by considering load profiles based on Portuguese transmission networks provided by ERS. We compute realistic transit times using a script used to simulate traffic conditions, and we consider two neighborhoods located at different buses and also different geographic locations. These are the tariffs based on EDP time of use tariffs and the Iberian day-ahead market prices for the summer and the winter. And by simulating this grid, we get the active power exchange for different scenarios with and without the coordination for the smart neighborhoods, for the parking lot energy management system. And we also analyze the energy losses in the grid, the power losses, the power supplied by the grid, and also the voltage profiles. The results of the first case study show that by applying the coordination, we get benefits in terms of minimized energy losses and also less energy supplied by the grid. And then we move on to analyzing the effect on individual EV owners. We track the state of charge of one electric vehicle for an entire week. And we can see that, again, by having this coordination, we have benefits not only for the grid operation, but also for the EV owners in terms of decreased electricity bills. So this concludes this chapter. This work is published in a IEEE conference paper and also accepted with minor changes in applied energy, full case study. And this revision was resubmitted. Now I move on to chapters 4 and 5, where instead of looking at contemporary models, we try to come up with completely new ways. Chapter 4 for forecasting and chapter 5 for power flow management. In chapter 5, a new probabilistic method is proposed to forecast renewable power generation. It is based on kernel density estimation and only relies on local and publicly available historical data. The main premise is from a historical data set, we find the most similar cases using kernel density estimation, and from there we conduct an in-tempo prediction to predict the new value. We do a real case study on PV installations located near Coimbra in Portugal. These are the specifications of the installations and also the public data that was available. This is the data for an entire year, which uses input for the model. The black lines are the real recorded values, and the yellow lines are the irradiance-based forecasts. We provide this data to the model, and we are able to get the predictions and compare them with a neural network and with a deterministic forecast. The proposed method is much faster, almost 40 times faster than a neural network, and provides better results for the vast majority of the cases. And it can be employed for local forecasting, for renewable power, but also for low demand forecasting directly. In the next chapter, this paper was published in a journal paper found here online for reference. It was already cited by 12 papers excluding self-citations. It was a very impactful paper, actually. And we use this method to expand it to a machine learning method in chapter 5 for power flow management in smart grids of the future, for the decentralized smart grids. We start by checking the history of how probabilistic methods evolved into machine learning methods. We divide we categorize the difference between probabilistic and deterministic methods based on this review. And then the new formulation is presented. This is very similar to the previous case, except here the activation functions for the most similar cases are saved in an activation vector, and this will become very important in the next 2 slides. This is the transition that we propose from centralized operation to decentralized operation. The historical log of the optimal control actions are passed on to local agents for each zone, and each agent only has access to information in their local zone. And based on that, they use the employed method to predict the optimal control actions in operation and operation planning. The activation vector can be used, and this is a major contribution of this work, can be used to have a cooperative information exchange platform between the agents to improve their control actions without sharing the raw data. And this is actually a major contribution of this work, and we investigated by simulating a case study. We have here 24 bus test system. We divided according to the conceptual model proposed. We used 1 year high resolution, so 15 minutes data from from ERS profiles, from the Portuguese transmission system, typical load profiles. And each agent, as we said, only has access to the historical optimal control action, historical optimal generation, historical load values only within its zone, the hour and day, so only has access to local and public information. We test this by trying to predict the optimal actions within 1 week, also with a high resolution. And we conduct 3 different studies. In the first, we check the influence of tuning the parameters, and we can see by doing slight tuning of the parameters, we can obtain an accuracy of less than 0.1% for all the cases, which is highly accurate. Then we conduct a comparative analysis by checking the power of the cooperative information exchange platform that we did. And we can see that even without tuning the parameters and by putting random parameters, simply by exchanging the activation codes in this cloud-based platform, we can obtain even better results and lower the errors further. So the impact of the cooperative information exchange is actually higher than the impact of the tuning of the parameters. And finally, to validate it, we compare with the neural network methods, and our proposed method is better. It provides much more accurate results and also higher computational efficiency. This work was published in a conference paper at CPE Power Eng, and also accepted with minor revisions in the International Journal of Electrical Power and Energy Systems. This concludes the second part of the thesis with regards to grid operation. The third part looks at end users and develops new models for energy management and planning, mainly energy management, to help guide this transition into from the point of view of end users, not the grid. Chapter 6 deals with residential sector, Chapter 7 deals with the transport sector, Chapter 8 deals with the industrial sector. We start by the residential sector. A new combined scheduling and consumer consumption and trading scheduling method is developed based on a new concept of energy value signal. So rather than scheduling based on the price, we calculate the value of energy. A case study to demonstrate this shows we have different prosumers, all in one low voltage grid, all providing bids for energy generated through local resources and competing with the grid itself. So the real-time prices provided by the grid. Each consumer would have their different loads that they want to schedule. They provide their preferences for the optimal time where they want these loads to operate. And the scheduling tool finds the optimal scheduling of each appliance, which also leverages the energy value for this prosumer. We see on the left the schedule, and on the right the scheduled load and the transacted energy, so the choice between buying from the grid or buying from other prosumers. And here the pink line is the energy value, and the objective is to raise it as much as possible. And this work was published in CEST 2019 in this paper for more reference. Then the next part deals with the transport sector. A generic public transport network is modeled, and all the parameters are included in terms of the charging infrastructure, the batteries on the buses, and the dynamic electricity prices. And the objective is to minimize the total ownership cost of this fully electric transport network. The constraints are related to the infrastructure, the batteries, the energy charge, and energy balance is shown here. And we test it in 3 different ways. First, we provide the parameters for the case study corresponding to current technologies and the average energy prices in the day-ahead market for Central Europe. And then we test it on individual routes. So here the algorithm is shown to be able to optimize the type and the location of the charger, the state of charge of the charging schedule of the bus, and also the energy charge per station. This is for the second route that was simulated, and this is for the third route. And then we can analyze here the breakdown of the total ownership cost. And then we move on to designing full systems where we construct a system that has 180 different routes. And we are capable of finding the optimal design of the system in terms of the charging infrastructure deployed, the battery capacities for each route, the optimal battery capacity in each route, and also the breakdown of the total energy, total ownership cost. The third study investigates whether this model can be used to analyze future scenarios. We investigate the change in technologies and the energy prices forecasted for a 2030 scenario. And by applying this to the simulated network, we can obtain the expected cost reduction for each route as well. And so this model deals with the electric sector, how an optimization function can be employed to optimize the design of the charging infrastructure and the design of the bus networks themselves, taking into consideration dynamic electricity prices being present. This was published in a conference paper and also in an IEEE Access paper as shown here. And finally, for the industrial sector, a novel method was proposed based on graph theory, in which a conceptual model for a task scheduling problem in modern industry is shown. We have a mobile agent that attempts to traverse a map and complete certain tasks within a map. This is the mathematical formulation, as I said, based on graph theory of the algorithm. And the main premise here is that whenever there's a task present, we try to attract the agent to go towards this node. So by traversing in the map, we try to come up with the optimal pathing of the agent such that tasks are performed as fast as possible and with the minimum movement cost, which also corresponds to the minimal loss in the battery on the agent. We do a very complex or very detailed benchmark analysis and limit testing to test the algorithms. It's new and it deals with a very complex problem, and also to determine the stability of the algorithm. We determine the best path finding tool to be used, and we conclude that it's Dijkstra in terms of the computational time and stability. And we simulated on a real world problem where we have an inspection problem for a real refinery site. And the objective is to patrol the site using the minimum energy cost and by spanning as much as possible of the map on one full battery charge. This is the simulation of the problem. And our model is shown to be better than other graph theory models that are used to solve similar problems in industry. And to test the limits of this algorithm further, we rerun the simulation with moving obstacles, so in a dynamic environment where other obstacles are actually moving in the map. And once again, the algorithm proves that it is capable of determining the optimal scheduling and pathing of the agent to minimize to maximize tasks performed on one full battery charge. In other words, minimizing the energy consumption. This concludes the third part of the thesis. This paper was published in IEEE and it actually got the best PhD paper award, first place. And it was also published in the IEEE Transactions on Industry Applications. And those are the two papers for future reference if you would like. Now, final remarks. I'm not sure how much time I have left, but I will try to go through this as quickly as I can. The final part of the thesis addresses the research questions. We have 6 secondary questions and 1 primary question. The first secondary question is: can individual and proprietary data models from the IoE paradigm be used to leverage DSM and DR services from individual prosumers and microgrids, thereby improving global operation of dispersed energy systems? This was answered in detail in chapters 1, 2, and 3, and the answer is yes, they can be used to leverage DSM and DR services from individual prosumers and clusters of prosumers and improve the global operation. Second research question is: can local fully decentralized optimization and data analytics functions enable global integration of demand-side flexibility in the energy market system operation and planning? And the answer for this is yes. This was shown in chapter 3 and chapter 7. The secondary research question is, the third secondary research question is: can optimal consumption scheduling of individual agents in a decentralized energy system result in global optimal operation? Once again, yes, and this was proven in chapters 5 and 6. 4, do centralized data models provide an effective and sustainable solution for the operation of physically decentralized energy systems? And this is shown in chapters 2 to 5, and the answer is yes, this is possible, enabled by cloud computing capabilities, machine learning algorithms, and secure communication infrastructures and frameworks. Fifth research question is: could new models be created and developed to enable a fully decentralized peer-to-peer energy information trading platform? This is answered in chapters 5 and 6. And finally, the sixth research question is basically part 3 of the thesis. In the future cloud-based IoT paradigm, how can energy management models be adapted for end users in different sectors? The main research question, which is a compilation of all those 6, is in the future cloud-based IoT paradigm, how can energy management models be adapted for end users in different sectors? And this is discussed throughout the thesis and in the different parts. The part 1 of the thesis, the introduction, defines the first part of this question, which is, can fully decentralized distributed data models based on IoT and peer-to-peer networks, so we define what that is, ensure techno-economic sustainability for electric power systems. This is part 2, and cross-sector end users is part 3. And the final answer is fully decentralized distributed data models based on IoT and peer-to-peer networks can indeed ensure techno-economic sustainability for electric power systems and cross-sector end users. The design models must adhere to the design requirements defined for the IoE paradigm. Now, the final conclusions of the thesis is presented in chapter 10, and then we move on to discuss prospects for future work. And I specify 3 main directions, typical, but 3 main directions where follow-up work on this thesis and on this research can go, and in fact should go. The first is from an economic perspective. We proposed very interesting frameworks and very interesting ideas that have a lot of potential, which is the value of information exchange, and this should be quantified in a cooperative operation framework and forecasting frameworks, and perhaps business models can be developed for this. From a systems research point of view, in chapter 7 and 8, it was very clear that there is a big knowledge gap and knowledge transfer gap between the electricity, the industry, the transport sectors and the industry sectors, and the majority of work in smart grid energy management systems is actually done on the residential side, and more research should be done to focus on multidisciplinary research in this regard, and investigate the synergies that can be obtained from coordinating the different sectors together. Finally, from a legal perspective, in chapter 1 and 2, we have shown that without proper legislation, there is no instigator to the scientific research and development for technologies that we have now. It was not possible to instigate research on them without it. And accordingly, if the scientific community is to pursue the development of these innovative multidisciplinary tools to accelerate the development of the IoE, proper legislation should in fact be enacted to prompt it. I've already shown the scientific contributions of the work. As a direct extraction, I published 5 journal papers, 7 conference papers, 1 book chapter, and 1 newsletter article. They already have 43 citations, excluding self-citations. So I'm proud to say there was a good impact by this work. In addition, there was overlapping research done on related topics, which resulted in an additional 5 journal papers and 6 conference papers. I list the references here, the direct references which have already been presented in the chapters. I also got a few honors and awards during my PhD work, and it was a huge honor for me to receive these recognitions, and I would like to acknowledge that. Thank you very much. I hope I didn't take too much time, and I'm happy to start discussing my work with you. Thank you.
Thank you, Mohammed. You kept the time quite well, so exactly 30 minutes.
Good. Happy to know that.
Good, good. Okay, so now we are going to proceed with the discussion, and so according to the order of the discussion and the way how the different members of the jury are going to intervene. So I'm going to ask Professor Gianfranco Chico from Politecnico de Torino if he is now capable to start his discussion. You know, you have 20 minutes for you and the 20 minutes for the candidate. Please, Gianfranco, thank you once more for your availability. The screen and the floor is yours.
Thank you very much. Can you hear me?
Yes.
Yes, I can.
Okay. So 20 plus 20 is 40 minutes, but I will not keep these first 20 minutes for me. I prefer to have a discussion, more interactive, of course. First of all, congratulations, because I mean, there is a lot of work really here, but also I appreciated very much the fresh writing style, which is very good for writing these things. And also, I mean, you have an excellent record of publications for a PhD student here. So this is indeed a signal that everything went quite well. The thesis is very interesting. I will have some questions more, you know, there are many, many very interesting and good things developed here. However, as you can imagine, when we have this kind of discussion, we will point out also something to improve. So this doesn't mean that the overall work is excellent, in my opinion. We will just go and find out anything that can be improved, even a little bit. So at the end of the story, I will also send you a very short document in which I have some punctual remarks on single words, other things, typos, and very few typos due to the overall work. However, let's start with some general questions. First of all, in your opinion, which is the difference between Internet of Energy and Internet of Things?
Well, the Internet of Things is the general concept. The Internet of Things refers to, I think if I may I go back to the slide so I can discuss this in detail? Because I did not have time really to go into the details of the slides. So
it was just a general impression. I mean, I'm not going to the definitions. We will go in other.
Yeah, but yes, I understand, but I prefer to answer this, let's say, as accurately as possible. So This is the formal definition of the Internet of Things. So let's start with the Internet. The Internet is a communication platform that connects computing devices, so computers or smartphones now, and in a way connects people through these devices, right? The Internet of Things moves this connection or extends this connection to things that are not by nature communication devices. Or computing devices, such as our microwaves even now are connected to the Internet. And this is really the main point of the Internet of Things, that we have point for things, everything is connected. The Internet of Energy is a result of IoT enabling of smart grids. So when we talk about the Internet of Energy, we are talking about how smart grids, which are basically modern power grids, affected or evolved through IoT enablement. That's let's say the formal definition and the difference between them.
Okay. And what is, in your opinion, the difference between internet and what we use for energy? I mean, when you are using internet, basically you are sending information by packages, something like this. However, there is one main difference that has to be pointed out in general, that I saw many parallels done from the world of internet, not Internet of Things, the internet for data and information, and the world of energy. A point here is that on the internet channel, you can lose one package. I mean, you have another package coming. But in the real world, you cannot lose energy. So this is one of the major points that have not been pointed out in the past when trying to do the parallel between the power system and the world of internet. So this is a point. When we are talking about data, including commands, including everything, so everything can come. If we want to push the parallel further and make a strict parallel between the world of internet and the power system, this is the major point in which we cannot lose a packet of energy. This is one of the real points.
Okay.
This was just a comment, I mean, and not a question. Another thing, it was very interesting to see an historical overview of the concepts and of the things. I have a few remarks here. First of all, I would prefer in your writing to have a little bit of restructuring of the first part, just to go, because the graphics are fine. In the first two sections, maybe the many concepts are mixed a little bit, so it lacks of sequential style. First of all, yes, okay, remain here because it's interesting. You have updated the distributed generation basically to the 1990. I will send you 2 or 3 references in which you will see that distributed generation, basically the first publication also in the IEEE transaction comes from the 80s, 81 and 84. Just the name was not exactly distributed generation. The name was dispersed storage and generation. However, the concept is really the same. So just to, let's say, put an initial part of the history to what you have correctly indicated, maybe this will be a complement. You will see the references.
Thank you.
Yeah, I'm also interested about this first reference of a smart grid that you have dated in 97. And which is this reference?
I don't think it's cited in the thesis, because what I did here is I did a meta-analysis of the Explore library. I think I have it in my notes, but
okay,
you are right. I should cite it in the thesis. Yes.
Yes, but also there's another point. If you go and see what happens here, the term smart grid was just introduced incidentally. So it has very few, if anything, to do with what we intended then to smart grid. So indeed, the first reference on IEEE, let's say, authoritative reference is of 2004. So all the period from 97 it basically is not what we intended. We can really think that the smart grid has been introduced in 2004, 2005 in the scientific literature, not directly in 97.
Yes.
This is just to, yeah.
I just want to say that this is absolutely correct, and it even shows here. So the dashed lines here indicate that we have less than 1 publication per year. And you are right, until 2004,
yeah,
there is almost no reason. Yeah.
2004 is the first one. I mean, 2004, 5 are the first ones that you can get. And the other one is indeed only a single publication that incidentally named Smart Grid, but it was on a totally different context. So while distributed generation, you can go back to 81 indeed, maybe with the same idea, or you can add the distributed, dispersed generation, as they called in that case. It was not distributed generation, but the concept was really the same. And so it was just, while for demand side management, of course, things are correct, and they started immediately with this proceedings of the IEEE, set up the terminology, and then it's what we are using still now. Okay, this was just to give a few hints, also a few comments on this. Then let me see another thing. Where is this? Did I lost my notes? Oh, here. Okay. Also in the first part, I would prefer to indicate more explicitly distributed energy resources and the fact that they are composed of distributed generation, demand response, and distributed storage, which is, of course, what you are using, but probably some definitions put at the very beginning would be useful. Okay. Then another thing, here I'm thinking about the general things, and then we can go to the thesis also to some points. Okay, in the conclusion, so one of your parts, you have, if you have your thesis, we can go at page 157.
Would you like me to share the screen?
Yes, why not?
Okay.
Because I have a series of things.
I have it ready here. I anticipated this, so can you see my?
Of course, yes, I can.
Okay.
You can
so
go
where should I
to
go?
page 157.
Okay.
in which you have, I'm not,
Yeah.
just a moment, I'm not seeing it now.
Like 157 in the PDF or 157 in the paper itself?
157, no, here.
In the PDF.
Just a moment.
I think it's in the PDF.
But it's not exactly the same in my case because it's conclusions of chapter 6. In my case.
Okay, so it's 158 probably.
Yeah.
It's 159.
Okay, okay. It's a couple of pages different. Okay, here you have indicated leveraging comfort levels and so forth. I would like to ask you more about what did you do with respect to the comfort levels? So where did you address this part? Because you put in the conclusion that you have leveraged these comfort levels. Where is the part in which you are addressing these comfort levels?
Well, I mean, this word can let's say, has a very large spectrum of meanings, though. But you are right. I did not really specify what this means. I was talking about the concept itself, and in the formulation, this is done by the framework that we have here. So basically, the user or the prosumer sets preferred times for each appliance. These are not strict like other home energy management systems do. So there's no, let's say, strict upper bound and lower bound for the operation. And basically what happens is, imagine that this is the operation time of one appliance. And this is the preferred time. And the more, let's say, this is centered around that, the higher the value of energy becomes in the global function.
Yes.
So it's optimized in this manner. It's not, let's say, a strictly constrained optimization, but rather it's attracted more towards what the user defines. And that is also why I decided to have it in this way. So instead of saying, okay, I want it between 14 hours and 20 hours, no. What the user says is, well, I don't mind it being here by putting 1 as a low preference, but I would really like it to be here by putting 3. I mean, 1 to 3 can become 1 to 10, 1 to 100.
Yeah.
And we can adapt that. But that's the concept, basically.
Okay,
and this changes from one appliance to the other. So, for example, for this appliance 5, the user really wants it to be in this time. But for appliance 1, the user basically is kind of indifferent. Well, I'd like it to be here in the afternoon, but it's okay. It can be anywhere. So it's not from 1 to 3, it's from 1 to 2.
So yes, that's what was my impression as well. So probably instead of comfort levels, you can talk about consumer preferences.
Okay. I mean, you are right, because usually in literature, comfort levels refer more to thermal comfort.
Exactly.
Yes,
Temperature
right.
to other aspects. Here is more indeed preferences that are. It is the title of your table also, reference to consumer preferences. So
yes.
Okay.
You are right. Yeah.
Then let me see here. Okay. Okay. Let's jump a little bit. Page 219, which is in section 9.1.
It's a long thesis.
Yes.
219.
As you see, I'm really trying to find out the micro spots, because indeed there is a lot of very good work. So
yeah, thank you so much. It's here, right? This is 219.
219, yeah, a couple of pages before.
Before, okay. So in chapter 8.
Let me see here, because I have it here. The numbering is not exactly the same. So so my idea of 219 is chapter 9. Yes, secondary research questions.
Yeah, so it's 219, but it's on the other side. It's double, yes.
Yes.
Okay. Okay, so second.
Okay, this one is
Yeah.
+2. Yeah. So the numbers I have will be +2. Good to know.
Okay, I got it.
The last paragraph, of course, things are fine. I would add also, since you are talking about demand response and these kind of things, also the market rules that are promoting the willingness of the consumers to participate. I mean,
Okay.
this has been the establishment of advanced communication infrastructures. Yes, of course. However, I think that one of the major drivers was also in parallel with this, the possibility of having some market rules that allow the participation. Without them, consumers cannot participate.
Yes,
So this is another small spot. Then, yes, these other ones are more.
I mean, it is mentioned in the chapter, but yes, it's not clear here.
It was just, since you have mentioned explicitly the point, I think that the 2 points can go in parallel.
Yes, yes.
Then, okay, let's go to some even smaller spots. So it's a section 451. And if you can go to section 451.
4, that's chapter, that's part 2, 4, 5, 1. Okay, here.
And in the first bulleted point, okay. In the first bulleted point, you are talking about, you're writing about wind power output.
Yes, I noticed that mistake.
Yeah, while the second one is solar irradiance.
Yes.
And so I got a little bit lost here.
Yeah, it's a typo. Wind should be solar. You're right. I noticed it after submission.
Okay, good. And also in the final bullet here is, there is, let me see. Okay, there is a power, underestimated the power output, then we don't know what.
Where?
In the last bulleted point here of 451, yeah. There is a then missing something here.
Yes. This is true.
It seems to be incomplete, just the sentence.
Yes, this sentence is not, it's a typo as well.
Anyway, I will send you a dedicated note on this so you can figure out where they are.
Yes. Okay.
Another thing, okay, just other minor things. In general, you should avoid using the variable capital P for price because P is power. So sometimes it's a little bit misleading, but it's just in a couple of equation 6.5 or the path. Then, okay, this is fine. Okay. Okay, here the other ones are indeed minor points. All the rest is just typos or something like this. Maybe one of the things is page 186 now. It has to be in your case. Where you have
186. Where? 186. So
when you are talking about breaking.
About?
Breaking.
Breaking. Which chapter?
186.
Section 186. Okay.
No, it's no page 186. Or 184 in my case, but 186. Okay.
Breaking. Yes, regenerative braking. Yes, in chapter 7. Yes.
Yeah.
Yes,
this has to be written bracking without the E. It's not breaking, it's bracking, as is written. I mean, in a couple of places.
Okay, I'll look into it.
Just the way to write it.
Yes, yes. I used LaTeX to prepare the thesis, and
yes,
there might be a lot of typos because of the lack of
yes, because this is a technical term, and sometimes the word processors take actions.
I'll make sure to review these things in detail.
Yeah. Now, I am interested in other more general aspects here because we saw a few things, and I'm interested in your industrial application, the one in which you had good performances with this graph theory model and so forth. And which is the rationale that you use to develop this model?
Well, it's actually, I mean, Professor Catalão probably remembers this very well. It started just as an idea. So I was doing research, let's say, on demand response applications and energy management systems developed for different actors, and I found very little work was done on industry. And all of the tools used for task scheduling are either very outdated or they are done in a very rudimentary way, let's say. And I thought, okay, like how can we generalize this concept? So the first thing I came up with was this figure, actually, 8.1, and it's okay, how can we model a generic industrial problem? So in all industries now, in any industry application, whether it's smart warehouses, inspection of very large sites with mobile robots, for instance, or these things, even ports now are fully automated. So in terms of moving the containers from one place to another, all of these industrial problems can be modeled with this same generic thing. It's the same thing. We have a mobile agent that uses electricity to move. So everything is electrified. And the idea is to traverse the physical map with certain obstacles in the middle from set departure points where the chargers are located, basically, and to go perform tasks that pop in and out of the site. And that's why it was also very important to model the dynamic obstacles, because without that, it's not really realistic. So it also had to work.
Oh, okay, please go on.
Yes, and then the thought process was, okay, and the difference between industrial applications and residential or transport ones, well, maybe not transport so much, but even so, we can say that industrial applications are, the field of operation is a physical field. We have an area, and it can always be modeled as an area. And I thought, okay, what better way to model this than a lattice, map using graph theory? Then, okay, let's find out. How can we use graph theory to find the optimal schedule? And instead of using, let's say, this was the last part of the thesis, so I decided to get a bit crazy or out of the box, as they say.
This is a very interesting point of this, because it's a little bit outside the other parts, but it's a very good contribution on the other side. So.
Exactly. So I thought, okay, since it's the last part of the thesis, maybe we can propose something completely different. And what I did here is I said, okay, if there are no tasks, if there's anything, within graph theory, what functions are used to determine, let's say, the fastest way to get from one point to the other? And it was the Dijkstra or A star, so the shortest SPFs, shortest path function. And I thought, okay, what if we modify the movement costs to correspond to the tasks being present as well? So if there's a task present at a certain location on the map, then it becomes very cheap, where the cost of moving through the square becomes very low. So implicitly, the agent will be attracted to go there. If you know what I'm trying to say. So it's very implicit optimization. There's no explicit condition set, but surprisingly, it worked extremely well, even better than, let's say, the deterministic ways of modeling this. It was actually a very interesting study. And yes, the results clearly show this. And on top of that, by doing this implicitly, we have very high computational efficiency. This can be applied in real time. And more so, and this is the last point, it fits the narrative. Because in fact, this optimization is done on the local level of each agent. The only thing that is shared between all the agents in a map, in the field, is the map.
Not yet.
So once one agent performs a task, they can, let's say, update the value of the heat function, which is illustrated here on this map. All the agents see this, kind of like Google Maps when we're going and it's updated. Okay, this street is high traffic, this street is low traffic. So we all see the map being updated, but we don't see each other's private, let's say, paths or private scheduling. And that's exactly why this fits perfectly the narrative. Okay, we can have fully autonomous scheduling. They don't need to have any coordination beyond this map being shared. We don't even need a central coordinator. All we need to do is physically update the task, and this is enabled by IoT because with the sensor or with communication infrastructure, it becomes a fully autonomous problem.
This is an interesting starting point also for future reasonings about traffic systems with the electric vehicles or something like this. I mean, because we have obstacles, we have all the kind of elements. Yeah.
Yes, and if I may, I don't know if I have time to say this, but there was an additional part that I wanted to do, but I didn't have time, and it's very interesting. We can include dynamic prices in this model. So by adding here, let's say nodes, virtual nodes in the graph, okay? So imagine here we had some virtual nodes that do not really correspond to physical movement, but corresponds to the agent staying in its place and charging.
Yes.
And if the electricity price is low, this path or this loop that we add can become the cheapest option or the lowest cost option with the SPF. And in this way, it will prioritize staying for 1 hour, staying for 2 hours to charge because the electricity price is low, than doing a task. And once again, it's a trade-off because if the task is becoming very urgent and it's been very delayed, then no, then the path to the task will become cheaper than the virtual path of charging. If you understand what I mean. So
yes, this is a opening a number of possibilities.
Exactly. But it's difficult to prove, or at least time-consuming to prove it correctly. I didn't want to just, let's say, include a basic study. I wanted to prove it correctly, but yes, there's big potential there.
Okay, good. Another point on forecasting.
Okay, which section?
More general thing, then you will find out the section. When we are doing this kind of forecasting, we have data, and then we have the forecasting period.
Yes.
The key point is always how much the data you have are old with respect to the beginning of the forecasting period. So yes, if you think that you can forecast hour 1 with the data of hour 2 with the data of hour 1, this is not feasible reasonably because you have to finish hour 1 to forecast hour 2. And when you are finishing hour 1, you're already in hour 2. Okay. So when you are forecasting data, depending also on the length of the time step, of course, on the duration. So which is your view on how many data we can have before the beginning of the forecasting period? I mean, do you need 1 hour? You need 10 minutes? What do you need also in perspective to forecast the next hours?
Okay, well, let me just confirm if I understand this question correctly. You are asking about what is the size or the volume of data that we need beforehand in order to accurately forecast the next step, or are you also talking about the resolution?
I'm talking about the resolution on one side and the anticipation. I mean, if I'm asking data to forecast what will happen in the next hour, I don't think I will be able to get data so easily. I will get data for yesterday or for 3 hours ago. It's not so easy to get data, real data of what happens. And also data are manifested when the time has elapsed. So I cannot make the calculation in 0 time. So if I need to put a value for the hour 2, I cannot use the value for the hour 1 in general. Unless we are thinking about having a time step which is so long and I don't need to have a precision so high, so we can do something more.
This depends on what we're forecasting, first of all, because yes, for instance, in chapter 4, we don't even have this problem because all the information that is used here is basically public information. We have information, let's say, from the DFS already, and we're not even using real measurements. We're just using, okay, in this time last year, we had this forecast of wind power, and accordingly, we generated X solar generation. You know what I mean?
Yeah.
And in this case, we use publicly available information. The only problem that we have is with our own production. And yes, you are right. So in the beginning, we will have, let's say, some transition between the centralized, between the deterministic models in this case and the machine learning or the probabilistic models. And in the case of chapter 5, between the centralized operation running deterministically and between the machine learning model on a decentralized way. But I mean, I did not investigate this in detail, and there is a big, let's say, issue, especially on probabilistic and machine learning models with overfitting data, underfitting data. We really need to analyze this. This was not really done. I assume that we are already transitioning. So I'm assuming these functions will be applied to, let's say, installations that have already been running for some time. They have, let's say, 1 year of data, and they can start forecasting based on this data. What I did investigate is whether the method is capable. Let me zoom in here. Is capable of capturing these high frequency fluctuations. And this is in terms of, so the second part of your question, the effect of the resolution. If I only give it average data. So I only gave the method this black line. I did not give it the high resolution measurement. And in the results, we see that we are capable, let's say, if we look here, even though the algorithm was only given this averaged data, it still managed to capture high uncertainty associated in the areas where we have very high fluctuations. So we can at least know whether there is some uncertainty to be expected or not. This is the first point. The second point is with regards to chapter 5. So as I said, I'm already assuming that we have an already running system and we are transitioning. So we already have the data sets available. And here, perhaps a solution for this is what they do in wind power forecasting, which is called hindsighting. So what we can do is in the beginning, we can have two algorithms running. Of course, as we go with the probabilistic algorithm, we'll have a deviation of the error because, as you said, each hour has some, even if it's a very small error, that is added to the data set. And with time, this error deviates or accumulates. We have an accumulated error over time.
Yeah.
And what can be done is we can have some hindcasting, sort of forecasting, to keep correcting this data by running simulations after this is done. So these methods are, the objective of them is to be employed in real time. They're very computationally efficient. But then we can use later on slower algorithms or slower predictions or even physical measurements to correct this data as we go. I'm not sure if this really answers or gives some insight in the question, but this is what I think.
It's okay. This was the kind of reaction I intended to have on your side. Yeah, indeed. Okay, I think that I still have a few minutes, but I think that I can leave the word to my colleagues in order not to use all the time. And then at the end, if there will be a few more time, maybe I can have another question. However, it's okay. Real congratulations on my side because
thank you so much. Thank you.
Very, very well written thesis, and the contents are strong. And so.
Thank you so much.
Excellent. Good. Okay. Thank you very much, Joao. Please, I give you back more.
Okay. Thank you. Thank you very much, Professor Gianfranco Kiko. So we should carry on. And so I would like now to invite Professor Xavier Contreras from University Castilla-La Mancha, and also to start by thanking him about his availability, his willingness to discuss this thesis. Thank you very much. So the floor is yours, the screen is yours. Please carry on.
Okay,
Go ahead.
thank you very much for inviting me to be part of this committee. And first, I would like to congratulate Mr. Lotfi, because it's a very ambitious work. I've seen very few times so much ambition in a PhD thesis, which is, I think, the objective to achieve and to reach. So in that sense, by reading the different sections and chapters that he divided into his work, I was amazed at the amount of information and knowledge within the thesis. So I have to congratulate both the PhD candidate and the supervisors, because I was truly impressed. So also in terms of the publications, which are highly ranked, derived from the work. Not many times I'm able to see this amount of work also published. So that should be the first thing I would like to comment on. Then basically I request clarifications, and sometimes I have some theoretical questions about these different chapters that you have. So going in first to chapter 1, to chapter 1 about demand response. There is one section called 1.4, the status quo of demand response and future prospects. And then you mentioned two different types of demand response, mandatory and voluntary demand response. Since this is in my opinion, this first chapter is kind of a dissemination type of chapter. So it's mostly for advanced or not so advanced readers that would like to illustrate, would like to know about what's the demand response and the relationships between demand response and the DSM, etc. So you mentioned mandatory and voluntary ones. In your opinion, although you have written but not that much, which one would you enforce if you were in charge of these the legal issues related to demand response, and you have the chance to decide yourself? I have an option to have a mandatory demand response, which you mentioned, by the way, it's kind of incentive-based programs, or you have the option to use a voluntary demand response, which is based on prices. So one gives incentives, the other one gives prices. You know that prices are mostly related to markets. Markets and prices are highly connected, and incentives, it's something that you may use to make people willing to use your type of regulation. So which type of regulation, according to the studies and to the study that you have developed in this section, in this chapter, would you recommend? Or if not, would you recommend some type of combination according to what countries, what the developing and developed countries, have done in the past? That's my first question.
Okay, thank you. Well, I would answer by saying that enforcing a voluntary program is an oxymoron. It's contradicting in a way. So we cannot really enforce voluntary.
You could say not enforce, but make it possible to happen, so that people would be aware and willing to use that. That means that they would have the tools to do that, not that you enforce to do that.
Yes. No, I just wanted to make this point clear. So in terms of enforcing the regulation, well, it's a bit contradicting, but what would I recommend? In developed countries, as you mentioned, with a highly functioning communication infrastructure, highly educated populations, and a stable economy, and that's very important, I would recommend voluntary demand response programs. So as you said, from the research conducted and up to my knowledge, it is better. For developing countries, especially in commercial, industrial, and transport sectors, I would recommend mandatory demand response, because the infrastructure and the know-how is not there to really get the benefits of voluntary DR. In fact, it might actually bring more harm than good. So yeah, it really depends on the economy, on the infrastructure available, and the know-how that is in the country.
Okay, thanks. Move now to chapter 2 about mostly about the Internet of Energy paradigm and the blockchain. And you divide blockchain 1.0, 2.0, 3.0. And then
Yes.
I'm reading on 3.0, you say, I'm quoting, a fully decentralized platform capable of autonomous operation relying on distributed mathematical models. This self-managing system can determine optimal strategies to ensure global benefit and thereby constructing smart contracts accordingly. So when you say relying on distributed mathematical models, what are you talking about exactly? Or what are you quoting exactly?
I'm talking about methods such as decomposition techniques, so such as ABMM, for example. And those would not be possible if there was no, let's say, way or enabler to securely exchange the local functions in a secure manner and with global consensus, because these functions, these decomposition techniques, are based themselves around global consensus. So blockchain, let's say, this level of blockchain implementation perfectly fits what these methods intend. That's what I was referring to here. So again, this is an introduction chapter, but that is what I'm referring to. But you are right. I mean, it is up there. So before these bullet points we see here, not in the bullet points. You are right. Yes. So I was talking about ADM.
Yeah, you mentioned blockchain 2.0 and ADMM. So I assume
yeah,
ADMM
so when we
is
combine
related to 3.0.
Exactly.
Okay, I see. Then I'm going to chapter 3, which is starting the application part of the thesis. And then I'm going to ask you things related to the model itself, not general questions like that. Oh, sorry. I'm missing one question before. No. That's correct. So going to section to chapter 3. You mentioned when you were presenting your thesis that you want to intertwine electric power and transport sectors, and then you have some pictures here. Are you talking about distribution system, transmission system, or both? Because when you talked about electric vehicles, I was in doubt whether you use distribution or transmission. I assume distribution initially because electric vehicles are connected to the distribution system when they charge, right? But is it that you mentioned transmission, or I'm wrong when you said that?
Okay, so 2 points here. The first, I'm not saying that, well, the objective was not for us to intertwine the two sectors. What I was trying to explain is that in high levels of electric vehicles cause an unavoidable intertwining between the sectors anyway. So this is something that we have to adapt to, and it's not something that we propose. It's a result of high levels of EV penetration. And in regards to the second question, that's an excellent question. It's on both levels. It depends. If we are dealing, let's say, with consumer EVs charging at home, that's on the distribution level. But when we start to look at aggregated entities such as electric vehicle parking lots and the new energy management systems for them, or aggregated smart neighborhoods, so large neighborhoods of smart homes, in this case, we'd be talking on the transmission level. So it exists on different levels of aggregation. The study that was conducted, let's say the energy management systems for homes were employed at the level of each home, but then they were, let's say, leveraged to a complete smart neighborhood and also the parking lot energy management system. And in this case, we modeled a transmission network.
Okay. Now moving to the model itself, where you have the HEMS, so you have several homes where you have these PVs, you have the chargers at home, and you also have the parking lot, the management system of the parking lot, in which they also have PV panels, rooftop PV panels, and both of them are connected themselves and to the power grid, which I assume, as you mentioned, that this power grid could be anything, right? That doesn't mean it should be the network in general, right? The electrical network. So now going to the algorithm that you propose, let's go. It's in my page 62, which is just before figure 3.4. So just for you to know. Just before that figure.
3.4.
Yeah, figure 3.4, just that page. Yeah, the page before that.
Okay.
Where you have several steps. So, well, okay. I know, well, I tried to understand, and I think I did, what each of the system means. And you say you generate first individual schedules for each EV, arrival, departure, and transit times. when you say generate individual, that means that, okay, because there are usually two schools for that. One is just pure simulation, and you make up the data according to your own simulations, or use real data. Which one are you in this one? Because it's not clear to me. Although you used real system, it seems like in Portugal, you have several cities. Did you use real data for arrival, departures, and transit times, and then you massage them? You dealt with them, because otherwise, it's. I think it's a key point. It's highly complicated to pick up every single schedule of electric vehicles. How did you manage with all these things?
Yes, that's true. And actually that question was one of the main comments we got in the revision of the journal paper here. May I go back to the presentation, if it's okay? Just to answer this question effectively, because I included it in the slides. Yeah, here. Can you see my screen now?
Yes.
Okay. So here are the schedules that are generated. Perhaps it's clear in here, okay? Yes. What we did is a bit of both. You mentioned two schools, and you are right. And what we did is, let's say, a combination of both. So we tried to make a synthetic case study, as you said, in order, for two reasons. First, because, well, it's more straightforward for us. And second, because it's better in terms of scientific publications to have something that is reproducible by readers, so they can build on it. But we assume realistic uncertainties of the transit times based on real traffic data from Porto. So we took two neighborhoods and we measure, okay, what is the transit time between this and this? You can do this on Google Maps even. So you can calculate the time in the morning, the time during the afternoon, the time at night, and it will give you different expected transit times based on real traffic data. So you can let's say, get more or less an estimation within the metropolitan area of what is the variation. And then we assume different types of schedules corresponding, well, this was more heuristic, but it's what we encounter at the faculty at least. You have people with morning schedules, people with afternoon schedules, and we do basically a combination of all of these things. And the script that we use to generate this data applies a random element as well. So you have different categories of schedules, different categories of arrival and departure, different neighborhoods that are different distances from the parking lot. And on top of that, you have some, normal distribution to add some random element into the schedule. On top of that, I'm not sure if it is shown here. No, it's not. But basically, we use typical load profiles. They are the same load profiles that we have in chapter 5. So we use typical load profiles by ERS, by the Portuguese Energy, the regulator services entity, basically, and the regulation services entity, basically, and those already account for self-consumption. And so we try to make this as realistic as possible, still without losing, let's say, it being straightforward and reproducible. I hope I managed to answer the question.
Yeah, I see it's complicated. Yeah, I see. That I expected. That's why I asked. Then, okay, going back to the steps, you generate the schedules, then you run the PLEMS code for the state of charge for each electric vehicle. So that means that basically this parking lot acts as a charger for the vehicles, and they exchange also power with the grid. Then you run the HEMS code for each individual home to determine the power exchange. And then you say in step 4, at each time step, run AC optimal power simulation for the power grid. So my question is, they exchange information. I assume this type of information is not proprietary. I mean, it's kind of free information they can exchange because they do not release private information that could harm themselves, or that could be couldn't be good for them. But then you also mentioned, and that's also in a picture, that there is an exchange of power of both systems, of the HEMS and of the PLMS. But then you show the results. And of course, the results are kind of, I mean, I would expect that in the sense that, well, depending on which one, which system are you talking about, they have different schedules, they have different objective functions. So my point is this type of coordination the best you can do with both systems? I mean, this is, in my opinion, it's an exchange of information between two systems in which both of them, they optimize their own objective functions by themselves, and they count on the other party information. Basically, that's what I understood. But then assuming that happens, is there any way in which you could make this system optimal in a kind of holistic sense, I mean, for all of them, or this is implied in the way you have solved it? Because, you know, usually when I say the systems, you usually say, okay, I have an objective function, you have an objective function, we will never agree, because all of us, they have, I mean, if I own a parking lot, I would like people to charge and to get some money. And if I'm a homeowner, all I like is to have to spend the least money I can on my chargers, and then go home and charge at home if the tariffs are okay for me. So they live in different worlds. But then you connect them, because in real life that happens. Have you thought of a way in which, because I saw the results that you get in the power flow analysis and all that stuff, and you know, there is a missing actor here, I think, and it's the electricity system. The electricity system, the network, the distribution or the transmission system, they would look for some type of cost minimization of the operation in terms of optimal power flow, let's say that way. So if you made them interact to each other, these three guys, these three systems, what you would probably create is some type of synergies, because if I were the operating the DNO, well, I think you call this the network operator, let's call it that way, or the DSO, sometimes they call it. I would request from you to respect my transmission or my distribution line limits, right? Because this is what I want. And in case let's say you charge a lot, and then you're charging my system and you're forcing me to do something I don't want to. That type of input that you could, like, for example, this type of constraints, to me as a homeowner or as a parking lot should be a constraint, but for me, it's something I have to enforce. And I would request you to do this type of thing to improve my system. So if I could use you to make my life easier, in the sense that I minimize the cost that I have to support all type of charges, loads in this case, I mean, you would be a load, because an electric vehicle, it's a load, a moving load, and a moving battery. It's a mix. It's like a moving type of storage device, call it that way. So it's a moving storage device, and very, very strange, because they are depending on the owner who is driving. So it's kind of it's a weird type of thing, but it is there in the system. So my point is, I think what I would like to see, and maybe it's future work, I just suggest, is just to put the network within this picture, because I see that the interaction that happens, it makes sense. But I think you're missing a part. And let's say I'm the distribution network operator, and I forbid you to do that because you are stressing my system, for example. That's my point. So I would like you to comment on that.
Okay, that's a very good point. Thank you. So let me start by saying that the parking lot energy management system, or the EV parking lot, does not only get money by charging the EVs. They can sometimes discharge the EVs, pay money, and participate in ancillary service. So there is, let's say, that this is already modeled. It's true that it was not investigated in detail, and as you said, it's an excellent point. What sort of incentives can the grid provide dynamically according to what's going on in this coordination to be a third actor, let's say? And yes, this is a perfect follow-up work for this. It was not investigated because the objective here was to highlight this coordination, the synergies, as you said, that make sense from this cooperation. But yes, this is important to consider. With regards to the EVs, yes, I mean they are basically batteries on wheels, so to speak. And yes, the objective functions are very different, and we maintain them this way because this is what will happen in reality. And no one is going to open an EV parking lot without their main objective being making profit, and no one is going to install a home energy management system or invest in a smart home without wanting to minimize their energy usage because of it. Each person wants some return on their investment. The way that this can be done, I would say, so what comes to my mind is for there to be some sort of dynamic changes in the contracts. So let me show you here in the cost function of the parking lot energy management system. There are different unit prices, okay, that are set as a contract between the EV owners and the parking lot, so the ones participating in the smart parking lot. And what can happen is we can make those dynamic. What can happen is there can be some sort of bidding back and forth between the EV owners, like, okay, no, if you're going to discharge me at this current time, I'm just going to go back home. So either pay me more for discharging my EVs or don't do it. So there could be this, let's say, two-way communication and another market between those two and also the grid eventually. In this case, it was considered static. The thing that I did to try to, let's say, consider this, or even, let's say, have it there, but in a very generic or general perspective, is I considered real market prices. So for the EVs, I consider time of use prices from EDP, okay? And I consider day-ahead prices in the Iberian markets. And in a way, this is a communication between the grid and the two entities, because the energy management systems would respond to these prices. It's part of the optimization problem. And this is the only way that this is reflected. But yes, this can be done dynamically, and we can investigate this and follow up work. That's my response.
Yeah. Well, just to conclude that part on chapter 3, I think I was expecting, but I know it's a huge thesis in that sense, so I know it may be too much, to have a more type of sensitivity analysis on what type of parameters would make changes in the system. You mentioned some things that make sense, in the sense that who is having more influence, whether the HEMS or the parking lots, and I saw that, so that's a good work, but I was missing this type of studies. Anyway, it's a comment, it's nothing else. So, because I don't want to extend more than the time I have allocated, in chapter 4, which is forecasting, well, first, something that struck me every time when I read it and I reread it again is why artificial neural network winter error is better. I was expecting that your method should outperform, but it seems like when you compare your method with the artificial neural network, I read it somewhere, that at least in one case in winter, the error was slower not in the ensemble forecast that you mentioned that you used, but in the artificial neural network. Is there any reason for that? I think you mentioned something about the different type of data you obtain for winter and summer, and that make a different dispersion, something like that. But do you have an explanation for that?
I have a possible explanation, and yes, you are right. There is one case where and it's in the winter, where the neural network outperforms our method. First, I want to comment that while the neural network outperforms it in this case, both have a prediction within reasonable limits in terms of forecasting renewable power generation, and both of them, the neural network and the kernel density estimation method, they outperform a deterministic, let's say, irradiance-based forecast. That's the first thing. With regards to the data, I use the data for the entire year. So we're trying to forecast 1 week from the winter, but we have very high resolution data, real data that was recorded from the PV installation. And I decided to, let's say, be very honest about the results, that, okay, these are the results, this is the data that we provided, this is what we have. That's the second point. My explanation would be here. And this was actually, as I said, chapters 4 and 5 are linked to each other. So it's first proposes, let's say, the use of kernel density estimation, and the other one completely extends it to a full machine learning algorithm. And in here, we did not tune these bandwidth coefficients for the kernel functions. We set them heuristically, let's say. So the smaller the value, the higher the correlation between this variable and the output. And we do that. So we say, okay, there's high correlation between, and we did it using correlations actually. So, okay, there's high correlation between solar irradiance and the expected output, of course. So this has the narrowest band for the kernel function. And basically do the same, but it was not tuned. That was done in chapter 5. And we highlight the effect of tuning those parameters, and it has a significant effect, not as significant as the cooperation framework, but still a significant effect on improving the results. I am pretty sure that if we do a study on tuning these parameters, this will no longer be the case. So that is my explanation for the winter case.
Yeah, I saw. And the other point is, and it applies to chapter 5, and is why you only compare with two other methods? Why not time series methods, the classical methods that we have used sometimes for this type of forecasts? Did you try, or did you think about trying? I don't know, any type of time series methods.
Yes, there are a lot of methods. Well, first, in this chapter, I make a clear distinction between basic, let's say, probabilistic methods, and I go into detail in the introduction about time series methods and point estimation. So I really take this all the way to modern machine learning algorithms. And in fact, machine learning is just an evolution of these probabilistic methods. The idea was, well, first there was a time limitation. I just wanted to compare. We have a decentralized case. I want to compare it with the centralized solution, which is the ACOPF solution that is obtained. And I thought of comparing it against a well-established method, which is neural networks, and also to be consistent with the previous chapter. We could have employed many more methods for comparison. In fact, a lot of the research work that was analyzed in the literature review does this. There are 5 or 6 other methods that could be used for comparison. And not only from the probabilistic category, but we can also use methods like ADMM to compare decentralized probabilistic approaches with decentralized deterministic approaches. That is also something that could have been done. Why was it not done? Well, first, time limitations, and second, to be as consistent as possible with the previous chapter. This work was just an extension of it, and it went in the same direction. But yes, in future studies, this should be done, let's say. So this paper, or the journal paper, proposes the method, and future work can then compare different sizes, investigate the scalability of the method, compare it to different approaches in that sense. So it's a follow-up for the work. That's the reason it was not done here.
Okay. Now moving to chapter 5. In figure 5.4, which is in figure 5.4 on my page is 118. That's it.
Yeah.
Well, yours is this one. Let me ask you something, because I read it and you apply this to an optimal power flow, if I understood, and you show the results. Fine. So I'm asking you now. Let's say I'm an old timer. I'm a very old guy who is basically trying to use a decentralized optimal power flow the old-fashioned, which is, okay, we split the area in different zones, and we use methods like these border variables or frontier variables, which means that when you have a flow between 2 different adjacent areas, you have to define 2 variables, one for each one of the sides of that border, making them equal as a constraint. And I run the good old-fashioned optimal power flow the way it used to be with decentralized multi-area optimal power flow. We have this type of decentralized model with good results, and that basically goes back to the 1970s, 1980s, like the auxiliary problem principle, the works on decentralized power flow, blah, 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 all that stuff. Now I say, okay, I'm the old-fashioned guy. You have to convince me that this exchange of information that you have in 5.5 is exactly the same as what used to be, like, for example, one area exchange information with the other area in terms of the flow that goes from one area to the other, and you make this type of information consistent? Or what I was missing in this picture, maybe it's my own interpretation, maybe it's my problem, is what type of information is exchanged between zones? I don't have it clear from your figures.
Okay. No, actually, it's much simpler than that, because in here, this relies on, so, okay, let me start by explaining the figure. So basically what's done here, and this is a generalized illustration of how the algorithm works. So we have a set of historical entries, okay, for past operation. And what the kernel density estimation function does is that it activates certain time instances in the past based on which ones are most similar to the current case. And the main advantage of this is that or the novel contribution is that it's actually very fast. So we can directly, let's say from 1 year, 5 years, 10 years ago, we can directly, let's say, activate certain entries in our historical data set. These are the most similar to what we are having now, what we're trying to predict. These, let's say, each one of them can have a code or a serial number or a timestamp. And those timestamps are what is communicated. So I'm an agent, you're an agent, and we're both trying to forecast or predict the best control action for the next, for a certain case that we have now. And based on my information, I find that, okay, X, Y, Z are the most similar cases to what we have now. You find that A, B, C are. And by exchanging those, we improve our overall prediction, because your data set can correspond to different conditions than what I have. And instead of just sharing our raw data, we can share the timestamps for the most similar cases without divulging any private information or raw variables, let's say. That is how the activation vector works.
But my point is, that assumes, or I assume, that there is some type of uncertainty when you run your model. Where is the uncertainty so that you need to rely on previous values? Which is uncertain in your system? The demand? What's exactly uncertain? To have to rely on forecasting?
Information outside of our zone. So, for instance, here we have a utility at bus 7, for example. Bus 7 doesn't really know what's going on in zone number 4, for instance. It has missing data with regards to the loads here. It has access to, okay, let's consider instead utility 1, okay? So utility 1 can measure, let's say, the observable variables that they have. So they have access to the load here on the same bus, and they can also estimate or have a recording of the loads that are physically connected to it. But outside of that zone, outside of this physical connection, which in the old-fashioned way, as you said, I don't think it's old-fashioned, but let's say in the other methods correspond to the border. Outside of those borders, that's the uncertainty. They have no information about the loads here, and instead of sharing this information, what happens is for each instance, we just share the activation functions, the most similar timestamps. And by doing so, the other zones are helping it find better predictions, reflecting the conditions that they don't know about. And at the same time, they don't share the raw information about the loads on those buses and other variables in general. So any variable outside of the zone is unknown or uncertain.
Yeah, because it used to be, for example, this IEEE 24 bus, that if you have a single operator of the system, he should be able to know everything, and he should divide the system itself in different zones so that you can exchange information. So you're assuming now in this new picture that whoever is in one zone does not know what is happening in different in other zones, right? That's what you are assuming.
Yes, and that's in line, let's say, with the concept. If we talk about the physical systems, this is more in line with multi-microgrid networks, for instance, where we have different microgrids being managed separately and they are connected to each other, but each one is, let's say, self-sufficient and self-managing.
Yeah, so, but this is different from what you show, because this is a pure distribution system that I assume should be run by a single distribution network operator. So that single entity should be able to know everything, because it's in charge of that, yeah, I'm assuming.
The idea is we want to make this scalable. So in here, whether it's different prosumers or different, and I'm trying to predict, let's say, the bids, let's say, as we did in the energy value signals chapter, different prosumers trying to predict each other's bids, different utilities trying to predict the optimal bidding strategy. In here, the operation of the system, as you said. So it's supposed to be generic and scalable. But let's say the idea is anything outside of this zone is unknown. Contrary, and I mentioned this in the text, contrary to a central operator that has access to all the information and then divides the zones for the sake of solving the problem. So it's a bit of a different concept, let's say.
Okay. No, I get it. I get it now. I have to go faster now. Let's move to chapter 6. How many minutes do I have left? Or?
Yes. Let me tell you that you are about to finish your slot. Okay. So you have two, three more minutes.
One or two questions at most. Thank you. That's what I was asking. Okay. I don't have that much problem with, I don't have problem with anything, but I mean on chapter 6, I found it's a very interesting idea about the social welfare models that we could discuss forever about that, because social welfare, it's a controversial issue. What is the value of social welfare? But let me go through one question I have only on this one. So just to conclude this chapter, when you show the results, that should be the preference for allocation. That assumes that it's tied to the type of social welfare that you have defined. Would you change that social welfare, results would also change, right? That's my point. So it's dependent on the social welfare function that you assume that this type of prosumer is using, right?
The results are affected by two things. They are affected by the bidding that's made by the other prosumers, okay, at the same time, and how these bids are in comparison with the grid.
Okay, I'm sorry.
There's a good opportunity or not.
Now what that was my only question is. So are we talking about equilibria? Are we talking about competition? Are we talking about, when I compete with other guys, would you say that the results show some type of equilibria by showing what each one of them is scheduling, assuming that the other ones are also bidding? Is it some type of equilibrium result, competing prosumers?
Yes, and actually the extension that I wanted to do for this work, but I didn't have time, it's not mentioned at all because it was not even touched, but is to apply some sort of game theory approach to decide on this bidding, how this bidding can actually be done, and whether we can obtain some global, let's say, benefits from it. But yes, that should be the case.
That was my understanding. And to conclude with chapter 7, which is one in which you mix some type of electric power transport system and charging infrastructures. My question is only about the TOC, the total cost that you have, the annual TOC, the objective function. You assume it's a summation of 5 terms.
Yes.
You are assuming that there is a company that owns everything. It owns the batteries, the buses, the chargers. I would assume that if you would like to have some type of business model, I may be the owner of the chargers and I charge you with tariffs. I may be the owner of the buses. Why did you have a centralized optimization for some reason? Or is it that I'm missing something in this model and this is a simplified version of reality? Because, it may, you may know better than me that, is it true that in this electric buses system, the bus company owns the chargers, for example?
That's a very good question. No, I did not think of decentralized ownership, which is definitely a very... it's an important factor to consider. The objective here was to minimize the total cost of the system. So we look at the system itself. It was not a simplified model because all of the parameters were considered. So the battery sizing, the length of the routes, the parameters of the routes, the the dynamic electricity prices. So it captured the entire system. But in terms of the cost, no, we did not consider that more than one owner may be sharing the system. And that's a very good point. I'm going to add this. I would like to investigate it, and I will add this to the follow-up work. But
Okay.
yes, I would call this decentralized
It's
ownership.
always good work. Always stimulates further research. Okay.
Yeah, that's a very good point.
Okay, I understand why it's complicated. Okay, thank you very much, and sorry if I passed my question time. Congratulations. Thank you.
Thank you so much. Thank you.
Okay, thank you. Thank you very much, Xavier Contreras. So we should move on. And now I would like to invite our colleague, Professor Marcelino Ferreira from IST, University of Lisbon, also starting by thanking him for his availability. And so please, Professor Marcelino, you have your time slot is 10 minutes, 5 minutes for you and 5 minutes for the candidate. Please, the screen is yours.
Okay, so first I would like to thank you all for having me here and to be with you. It's my pleasure, and to thank the advisor for that, Professor Catalão. I was kind of overwhelmed by this work because it is so broad and so comprehensive and touches many things. Okay, so I would say that in that regard, I must congratulate the student for the work he has done and many papers he has published, and also the advisor. So I could say perhaps this is science at its best, okay, modernly speaking, and it kind of shows, even shows off, some substantial engineering knowledge and insight. And also the contributions, which are many, and in a thesis, I would kind of be happy just with one contribution, a single one. Okay, a contribution that say, well, this is something that makes an advancement or that somehow proves an important point that is interesting to know. So it would be just satisfied with a single contribution. And here you have so many that's kind of overwhelms me. So maybe the first question, well, I have very limited time, but let's say succinctly, can Mohammed tell me what is the single most important contribution he has achieved?
Okay, that's a tough question to answer. I will try my best. I would say the single most important contribution is the new frontiers that are pushed by the work on different sectors. So we here try to push, let's say, the frontiers and the developments on different sectors of end users, on the way that grids are operated, the mindset behind operating the grids and going forward to the new paradigm. And I would say this is the most critical contribution. As Professor Kiko, for instance, mentioned on the industrial problem, we come up with completely new ways of thinking about the problems themselves. And I think that is the most important contribution, providing a new mentality for tackling these problems.
Okay, thank you. You know, I must tell you that while reading this, and I'll start from the beginning, almost from the beginning. So let's just take a look at the abstract. Okay.
Okay,
Just one page abstract. That's good because it's just one page. Okay.
here we go. Oh, wait. Here, there we go.
Okay. So I come from, can you make it a little bit bigger? Yeah. So I come from kind of old school already, old school. And so I take a look at it and see, well, I start reading technological advances are enabling this suitable information and communications are needed to operate. And then third sentence, this is accelerated by increase in sustainability. And then I'll take a look at this. I see, what is this?
Where? The third sentence.
First paragraph, third sentence, beginning of third sentence.
Yes, this is accelerated by increased unsustainability.
Right. So what is this?
That the traditional models that we have to solve problems in power system operation and in the energy sector in general are becoming more unsustainable and unsuitable as systems are becoming more decentralized. So they need to be adapted. So traditional models, traditional mindsets of managing end users in the different sectors.
Mohammed, are you reading something?
No, I'm trying to explain the.
Mohammed, I'm reading. I'm reading
Okay.
one sentence, the first paragraph, and I can't figure out what is this. This, you know, grammatically, what is this? This, what is grammatically speaking?
Ah, okay.
What
I
is
got
grammatically speaking? What is it? Is it a noun, an adjective, adverb? What is this?
Okay, so you're referring to what this refers to.
No, I'm saying grammatically.
Okay.
Let's decompose this in portions. Grammatically, what is this?
It's a pronoun, I think.
Pronoun, yeah. So it's a demonstrative pronoun. Okay.
Yes, exactly.
Which is terrible. When writing science, you shouldn't use demonstrative pronoun. It's a key rule.
Okay.
Instead, you should use what? Instead, you should use what? You should use determiners.
Exactly. What exactly I'm referring to, I should be explicit.
And this is not a determiner.
You're right.
Okay, so the thing is,
yeah,
in spite of all that, which is not good in writing, there is another thing. Is this is singular. And if I look at the nouns before, all I see is plural, technological advances, blah, 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 suitable information exchange, data analysis, and blah, blah. And then you say this what? When you
the
say
acceleration.
this, you are referring to what?
The acceleration.
The what?
So let's say that, okay, I get your point. So no, first I talk about how, decentralized systems are competing on larger scales with their centralized counterparts due to technological advances. Then I explain.
I'm giving you the chance to correct this, to remove it, and substitute by something else. So what are going to substitute it by what?
I would actually change the order of the sentences, because in the first sentence, I talk about how decentralized systems are becoming more competitive compared to centralized. Okay, so then I explain what.
Mohammed, this is the
change the order
of a paragraph. It has nothing to do with the
Second.
first, right?
No, it should be referring to the first sentence, and it would make more sense for the second one to go in the third place.
So you
I
could
would
say
change
like
the
this
order.
stuff. Suppose you say this stuff, it is accelerated.
No, I would say this the fact that they're becoming more economically competitive. That is the
Okay, so you substitute this by the fact that they are becoming more economically competitive.
or this fact. Yeah, so that's why I would put it second.
They is what in that case?
The decentralized energy
Pronoun
system.
again. It's again a pronoun. Okay, that scientifically is not good to use pronoun.
Yes, it's true, especially in an abstract. Yeah, you're
My
right.
advisor would not allow me to use pronoun. Okay, so that's okay. So when you get to the end, then you can do something else. So the last paragraph, you say, well, last paragraph you cut short. It doesn't tell me much about the whole idea. There is no punchline in the last paragraph. And I was expecting a punchline. But other than I look that grammatically speaking, something else. Let us say, first sentence, the full spectrum and dimension of this transition. Okay, now we have, let's say, good. I say good. This is good because now we have a determiner. The same word, this, but now as a determinant. This transition. Good. But then I look, what transition is he talking about? It was not mentioned before. There was not before mentioned the word transition. Not in the previous sentence, not in that sentence, not in any of the other sentences. Transition is the first time it appears here in the text.
Yes.
And you say this transition, I say, well, he's talking about this transition, but what transition is he talking about? Was never appeared before. So I say, now he has a determiner, but this determiner determines something that never appeared, which is a transition. So can you correct for that?
Yeah, I would put in here, so you're right, should be the work in this thesis builds on architectures, approaches, and emerging technologies in the transition to the IEEE paradigm. And this is the transition that I am referring to.
Right. So this is something that I see you are a prolific writer. You are an excellent writer. We have written a lot. But
not good enough.
From old school, and I don't tell you that's the way you write is wrong. Okay. I was just telling you that as far as grammar is concerned, for those of us who care a little bit about the grammar, or the grammatically sound sentences, this looks terrible. Okay. Now, the other thing I was referring to in the abstract is the punchline. I don't see a punchline in the paragraph. So for a thesis as rich as yours, with so many content, so many things, and this goes back to the first question I asked, which was the single most contribution. Here I say, what is the punchline?
It will go here.
So you say, well, this transition 1 and 2. That's it. Ran out of space. I don't have a punchline.
Basically, my response to your first question should go there in the end. You're absolutely right, and it's very important. I mean, you are right about it, because the main objective of scientific research is to communicate. It's true. It's lacking there.
Okay, Mohammed, let's look at figure 2.5, please.
2.5. Okay. So that's
Professor,
section 2.
Just to let you know, sorry to interrupt, but don't forget about the 10 minutes. They are already passed.
I always start, okay, so
Okay,
2.5, yeah, real quick, yeah.
Okay.
please do.
2.5, okay, so this is a picture that is kind of familiar in many contexts. Well, you have something on top, okay, here is a cloud, okay, inspiring like, well, the typical thing is on top you have a coordinator or a master or something, and below you have the elements. Just, can you make it a little bit bigger so that I can see it? Below is the, yeah, thank you. Are the nodes, yeah, and something. So this is like coordinator, and then the coordinated, the master problem, and the sub problems, okay? So this is a picture that looks like that. Even though in this case, the master lives somewhere in the clouds, okay? Or maybe even above the clouds. Well, that's amazing. But it is similar picture. And then there is some communication where you have sigma 1, sigma 2, sigma n coming down and going up to the cloud. You have m1, m2, and mn. So this is so much like the composition problem, the master problem, sub problem. And in particular, this reminds me of a very important issue in scheduling, where you have this maximization problem. The top problem, master problem, is a maximization, and the sub problems are minimizations problem. Are you familiar with this analogy or not? Maximization on top, so the master problem is a maximization, and the sub problems are minimization. Are you familiar with that, Mohammed? So I was cut off, I guess.
Hello? Yeah, I'm so sorry. Disconnected. Can you hear me?
Hello?
Yes.
Yes, we are hearing you.
Yeah, I'm sorry, it disconnected.
So
No,
you
we
missed my question, right? Hello?
Yes, the last thing I heard was we have a master in the clouds, and then that this looks similar to decomposition techniques, and then it was cut off.
Yeah, okay, so master and then the sub problem, right? Master problem and the sub problem. Okay, so this is similar to what happens with this, for example, Lagrangian duality problem, where you have the dual problem, solving dual problem on top, and then the dual function evaluation on top, on the bottom, sub problem. Are you familiar with that?
Yes, I am. It looks similar to it, but it's not the same thing, no. And this reminds me of the toughest question I was asked when I was proposing this topic by Professor Matos and Professor Pesas Lopes. And they asked me, okay, in this cloud system, who owns the system? And my answer was no one. Ideally, the idea is that there is cooperation without any central operator or owner being there, which is very much similar to how decentralized economies running on blockchain are operated. No one owns the system. This figure, let me share the screen again. I'm so sorry I disconnected. This figure was supposed to augment this part, but because I was trying to organize the theses, it ended up being in the end. It was supposed to augment this part. So to separate between the different levels of decentralization. So we can have, let's say, a centralized system with large generation centers that is being operated in a decentralized way, or the opposite. We can have a system that is...
But let me go more specific. Is there a higher level at the lower level or not? Is the
ideally what we are trying to reach is no.
Yeah?
Ideally, what we're trying to reach eventually is no. There is only...
In that picture, can you show the picture again?
Here.
in that picture, the cloud is above, is at a higher level. But this is just a picture. It could be at any level. So the nodes are in no way coordinated by the cloud services.
No. No, they share the services. So they all share the same services that are available in the cloud, same way we all use map services or weather services. So we share this information.
This cloud should be in the middle of these nodes.
Yeah, okay, yes. Yeah, yes. From the first look, it does seem like a hierarchical algorithm or a hierarchical structure. Yes, you're right. Now that I look at it from far away, yeah, it's true. It should be, let's say,
but it's not. Okay, it's
yeah.
just a question of sharing. It's like a common service.
Yeah, exactly. Yeah.
Okay, so Professor Lopes, I would say that I'm pretty much finished with that, but I just want to return to the beginning, which is I'm overwhelmed by the amount of work you did, and this is fantastic. Okay, it's tremendous work, and I don't know how long, how many years, let's say, did you take to come up with this series?
Well, I would like to measure it. I was just speaking to Professor Catalão yesterday, and it's been exactly 4 years and 1 day since we started working together.
Okay, so
So
you worked pretty hard. Okay,
yeah.
I would say congratulations to both of you. Yeah.
Thank you.
Okay, thank you very much. So we should move on and try to keep the time. So we are now going to pass to Professor Carlos Engler Antunes from the University of Coimbra. So once again, thank you very much for accepting this job. So Carlos, the floor is yours, please.
Okay, thank you. Thank you for the invitation to be a member of this jury, and congratulations to Mohamed for his work. I'll do my best to use 5 minutes of my annotations that would lead for a nice discussion during at least 2 hours, but I will make my synthesis power as powerful as I can. So I will jump. Lots of general considerations have been made. I just wanted to say that I consider the thesis is quite well written and well organized. I found it a bit too long, namely chapters 1 and 2, which are too narrative. They could be streamlined without losing the main picture. So I will jump to chapter 3, to the mathematical model, and I will devote these scarce 5 minutes to mathematical models. I'm very sensitive in everything, but namely in PhD discussions about the formal correctness of the models. And I think in this case, the models are in general okay, but there are several inconsistencies that I would like to discuss with you. In chapter 3, I found that annotation section is missed. So annotation section would have helped to read the model, stating in a clear way at the outset, before presenting the model, which are the settings, the indexes, the parameters, and mainly the decision variables. For instance, on page, and the notation you used is quite cumbersome, is what we can call a killing notation. So it impairs reading the model in a straightforward manner. For instance, on page 52, you use 4 capital letters for an index. Okay, so EVID, you can argument that okay, it's narrative, but mathematical models should be economic. So mathematical models, as other models, should be elegant. Okay, and this type of notation does not help reading the model in a straightforward manner. So, for instance, here you are using 4 capital letters for an index, which is not good practice. Please, if you can go for page 54 and then 55, can you enlarge a little bit? Okay, thank you. So on page 54, I think there's 54, I'm referring to the numbers. This is 57. I also
54 is 56 here. There is like
54. Yeah. You see that in expression 316, you have a delta T that was never defined. I guess it's delta T PL, where PL.
Yes, that's a typo. Yes, that's a typo. Yes.
Parking lot, yes, but there are some issues of this type.
Yes,
since you don't have a notation at outset, we never know whether it is a typo or another entity that you made into the model. So in expressions 317 and 318, these expressions are not linear, as you recognize. And they can be only enforced to be linear by the introduction of, it's not difficult to do that, of course. They should be enforced to be linear by the introduction of auxiliary binary variables.
Binary variables, yes.
Set of constraints, that is to say that as they are, this is not a MILP model. This is not a mixed integer linear programming model because these components are not linear. They can be made linear by the introduction of auxiliary binary variables and sets of constraints. But for me, the worst part in this model is the objective function. You see on page 55 at the bottom, this objective function is completely unreadable. You cannot, even with a bit of imagination, you cannot read the objective function because you don't know, you don't have an explicit expression that gives you each one of these terms, each one of these entities. And even if you use the table that is at the beginning of the next page, trying to figure out, you see that for instance, IN1T is not equal to the variable that appears in the second column multiplied by the cost, by the unit parameter, because the cost parameter is cost is money per unit of energy. So you should multiply by delta T, which is the length of unit of time, for this be consistent. Okay. So because only this P multiplied by delta T is energy that then should be multiplied by a cost of energy. Moreover, this P never appears in the model. This P is nowhere in the model.
This one.
This one. Okay, so with the AN, you see that there's a AN, which I think accounts for energy, and this entity appears nowhere in the model. So the model, okay, it's here and it's connected to the PL2G. Okay, I missed that because the notation
is explained in the text. But you're right. Yes,
you are right. Okay, if there was a notation at the beginning, it would make it easier. Yes. In that way, I should pick up between the lines and the sentences all the decision variables. Okay, thank you for shedding light on this. So since my time is quite scarce, but maybe it would be more clear to state the objective function in a more explicit manner. Okay, so the objective function, which is a crucial entity of the model, to appear clearly in the model. So I had other questions regarding the interpretation of some results. I found the results interesting, and they would raise some issues, but we do not have time. So I jumped to chapter, I enjoyed chapters 4 and 5, although I'm not a specialist on forecasting issues. Chapter 6. I must confess that I depart to the reading of chapter 6 with some prejudice. I must recognize that, because I found this way of modeling consumption using utility functions a kind of black magic. If utility functions are not rooted on empirically or with strong or theoretically with strong axioms, I think utility functions are more or less useless. They give what we want them to give. Okay, and so on chapter 6, for instance, on page 147, I think there are lots of entities that are not quite defined. For instance, expression 6.2, but there are others. Key 2 and Q2 and Q0 are never defined, or again, maybe it escaped me because there is again no notation at the beginning of the section of the chapter in this case, but Q2 and Q0 are never defined. So it was very difficult to read the flow of this model so there are several entities here using these expressions. We are not defined. So the same happens with C and the gamma. There's a gamma, but there a gamma B with an subscript B appears. And I must confess, I could not find anywhere a comprehensive explanation of the entities that made up this flow of equations leading to this approach. So, but this is a formal aspect, but my main criticism here is that without a very strong, verifiable empirical background or theoretical development based on axioms, on strong axioms, in my opinion, honestly, this is how consumption models should not be done. Okay, so in my opinion, consumption models to be integrated in the optimization models should be based on physical operation of appliances, on the physical phenomena occurring in the operation of appliance, and on consumers' behavior. For instance, what you mentioned, slots for operation of shiftable loads. Okay, and in this respect, it puzzled me a bit talking about demand response without considering thermostatic loads.
Okay.
Because I think thermostatic loads are key to exploit demand side resources.
Yeah, okay.
Okay. So I don't know if you have some issue. I can then send you some notes.
Yes, please. Yes, please. Thank you.
And then analyze in a critical way, of course, regarding these issues in the models. Just a final issue regarding the algorithm on page 197.
197.
Yeah,
Can you tell me the section number? Excuse me.
It's page 197. So the numbers that appear on the pages, the algorithm 1 there. I must confess, I tried to follow the algorithm. Yeah,
Yes.
Yeah, in the Dextra. But I tried to follow the algorithm, but I must confess I couldn't, because there are some entities that I imagine they are external to the process. For instance, let's see the main cycle while,
Okay.
and the control variable is running. Okay, which should stop the cycle somewhere. But this variable appears nowhere and is not changed. So the cycle runs forever.
Yeah, but in a lot of algorithms, let's say there is a lot of algorithms even start with while one. It basically means that this is continuously running. That unless the entire program, the entire algorithm, or the entire process is interrupted by an external force, this is running continuously. So there are a lot of algorithms that have a condition of while true or while one. This is common in algorithm descriptions. So yes, the main point here is to indicate that unless an external interruption happens, this continuously runs. It doesn't converge, it continuously runs. It's a continuous algorithm. That's precisely what is intended.
So it's more a process in which an algorithm is embedded than a formal algorithm, because in general, an algorithm should have a stopping condition. And the stopping condition, as you said here, is external.
Not within an object-oriented programming environment. So if we are programming, let's say, a class and an object that is created within, and this is how modern, let's say, algorithms are designed, not necessarily, no, because this is encapsulated within a bigger process.
Yeah, so maybe I lost the entire picture, or the entire picture is not.
If it's a standalone function, then you are right. But if it's an algorithm designed to run continuously, such as the algorithms that we have in all web applications, basically, they are continuously run unless it's interrupted by like a failure of the entire platform. Then the algorithms are designed to be continuously running, such as reactive programming tools, such as I don't know, any web application.
Let me ask something there that I did not understand. What's the role of the tau there in the algorithm?
There are two different ways of counting time. So there is physical time, which is basically the global variable. This is shared by all agents that are traversing. And then there's tau, but this is explained in the text, by the way. It's here. There's an entire paragraph for it.
Understood. The role in the algorithm. Now,
the role in the algorithm is
how is it manipulated in the algorithm?
Tau is a traversal. So every time the robot goes out to accomplish certain tasks and comes back to the charging station or to the starting point, that's tau plus equal 1. Tau is incremented. So every cycle is 1 tau for each agent. And then this is not global because each agent can be at a separate cycle, basically.
Okay. And in line 18, what is happening in line 18?
Once it reaches the station, it updates. So we say here that the agent is actually reached charging station, reached the top, and we update tau plus equal 1. So this is, let's say, the idea that here, there are two options. In every step, there are two options. Either you're still inside the path, okay? So you're updating the map as you go in each point, okay? Or you reach the starting station. So in this case, you start a new traversal.
Okay.
That's exactly what happens. So if you follow this conditional statement, so once you reach the station, you said that this is true, and then you update tau, okay? And then you skip this else. In here, you update the entire global map, so this is for synchronization, and then you skip until the next traversal. This is the last condition before you go back.
Yeah, just to a last question before a small comment on the conclusions. Can we go to page 150, please?
150.
Yeah.
150 or 115?
50, yes, 50. 150.
Okay, this one.
It's where. Can you enlarge a little bit, please?
Top or bottom?
Sorry to interrupt, but we
that's just an issue where you say that there's is assumed the contracted power. What is there is not contracted power. What is there is energy. So unless you consider that it's constant for a period
it's
of
stable.
1 hour, contrasting power of 1030.5 kilowatt hour.
Yes.
It's
Oh, no, this is a typo.
Okay.
This is a typo.
Okay, so it's
Kilowatts. Yes.
okay. So a final word on the. I found the answer you give to the research questions quite well organized, quite convincing. It seemed to me at a certain point, in some of those answers, that they're a kind of re-engineering. That is, the answer was there before the question. But okay, formally it was completely correct, and I congratulate you for the amount and the quality of your work. I will send you my annotation, so I
Yes,
had
please.
more that
Can
would
I-
give interesting discussion, but the time is very scarce.
Yes, if Professor Peter allows it, I just want to say something quickly. So with regard, okay, very quickly. I agree with you 100% that mathematical formalism is extremely important. And actually, I did put a lot of effort, and I always do in my papers to guarantee. I did.
Yeah.
And a lot of the issues that you raised were actually fixed in the journal paper revisions. So I just want to say that those were fixed after the submission of the theses, and I completely agree. And I did put a lot of effort to avoiding this. But thank you for.
I just raised the issues because I know and I recognize
They are important.
a lot of care on that.
I did, and thank you for emphasizing.
Thank you very much. Thank you, Carlos. So we need to proceed, and please understand me that I also need to keep the time, and so this is a difficult job with such a rich thesis, but I need to do it. This is also my job.
Of course.
Okay. So I would like to ask Professor Manuel Matos and to leave him the floor for the next 10 minutes, please.
Okay, thank you, and thank you for being invited for this jury. Mohammed, you presented a big thesis, which is a multiple thesis because it deals with many things. I think that there are perhaps too much things at the same time. So it will not be necessary to have all these chapters, all these models, and so on. But you decide to do it, so it's okay. But understand that this loses a little a global idea of the thesis because there are many separate things. Now let me just add something of what Professor Carlos Antunes said about the research questions. When I read the research questions, I had the idea that the answer was there before the research questions were defined, but that's not important. It's just to agree with him. And one thing that is remarkable is the number of papers that you associated to the thesis. Of course, not all are accepted yet because it's normal due to the time needed for that purpose. But we accept papers in journals, so 10 papers in journals, 5 of them extracted from the thesis. That's what your explanation. And the fact is that besides you and your supervisors and co-supervisors, there are, in those 5 papers extracted from the thesis, there are other 9 authors in total, some of them in various papers. My question is, what did they do for you?
Well, in my main papers, I could have just said that I have 10 papers in 13 conferences or whatever, but that would not have been ethical. Hello, can you hear me?
Yes, yes.
Yes, that would not have been right, and I would not feel right about it. That's why I made a clear distinction between what is directly extracted and what has been part of overlapping research and extensions of the work. And I clearly list this distinction. In the direct papers, in the main papers, basically the co-authors. I could have just said that I have 10 papers. I can hear myself, I think. I'm hearing my own echo.
I hear you twice.
Okay. Yes. So in my own papers, I mean, the people in the work either contributed as a supervisory role or they had a role in validating the results. In some papers, some of the authors were providing the data and helping analyze the input data. But in terms of developing the models, in terms of the hypotheses of each paper, in terms of running the case studies and drawing the conclusions, in those papers that I mentioned that are direct contributions, I was the one that wrote the papers basically and did the work. So that's what I can say. In the collaborative papers, it's different. There are some cases where I'm working, for instance, with some of our colleagues at Inesk Tech, and I would be working on some analysis of the result, or I would be working on formulating the hypotheses or the conceptualization. It really depends. Every paper is different.
Okay. In fact, in the overlapping research, your term, the papers, there are also 14 authors that collaborated, but there we understand better the position you worked on projects where...
Exactly, I was going to say this.
Yes, okay.
Exactly.
Well, there was an enormous quantity of things that I would like to discuss, but I will not do it because there is no time, just to repeat what the previous members of the jury said. But the question sometimes is not clear about the meaning of decentralized here. If is decentralized methods for obtaining certain results, if it is the decentralized organization of the power system. There is a big source of discussion there, but as I said, I will not do it. I just I'm missing here. Okay, it was in the other page. You, in page 51.
Page 51.
Since you have the, you present 4 scenarios.
Yes.
But then you compare the result in scenarios. What is the meaning of scenario for you that you use here?
It's a situation. It's a situation where we have an energy management system installed in one place, but not the other, or no energy management systems installed at all. So there are different situations.
There are different situations. You compare the situations to reach what conclusion?
As I think it was Professor Contreras that pointed this out, it's to really dissect the contribution of each energy management system towards the results that we obtain. So, and also he mentioned that different parties are from completely different worlds. And I think this is evident. This is just an example, but for instance, here.
So in fact, these scenarios do not represent possible futures as usually scenario.
No. Scenario 1 and 4, and I mentioned this clearly in the thesis. Scenario 1 is the base case, and scenario 4 is the one that we want to compare it with, and both are possible scenarios. Scenarios 2 and 3 are the ones that are used as control scenarios, let's say, intermediary scenarios to really measure the contribution of each of the energy management systems. But 1 and 4 are the two main scenarios that we are comparing.
But so scenarios, your scenarios include making decisions.
No, my scenarios include comparing the synergies of having different things making decisions at the same time.
That includes making decisions. That's in page 157.
5, 7. I'm sorry. 1 to 5. Okay, here we go.
You say, rather than minimizing energy costs, we maximize energy value.
Yes.
Okay, so my question is, what is the consequence of this? I mean, you have a solution then that you obtain by minimizing the energy costs. And then you change the paradigm and obtain the best solution, the solution with higher energy value. And how this reflects in the energy costs?
I can say the direction that I was trying to go towards, okay? And I will actually quote you and Professor Pesach Lopez from an S-Grids meeting. When you were talking about eventually having the kilowatt hour as the unit of exchanging energy and not a euro or a dollar, that an energy unit is in itself something with value. And we were discussing this, and this is the direction that I was trying to go towards. I could not really formulate this mathematically all the way or really reach that conclusion, but this is where I was headed.
Okay, but it's important to understand that when you have a principle that you are following, and then you change to another principle, you continue to be able to measure what happens in the old principle. Can say when I maximize the energy value, the cost will not be the minimum, but in compensation there will be this or that. That was the kind of development.
Precisely.
Perspective, yeah.
Precisely, yes.
Manuel, please try to conclude as soon as possible.
Okay, so as soon as possible is now, but let me ask first, your thesis uses many concepts, many buzzwords, many new things, many new tendencies, and that's okay. Let's explain. But there is something that you never use is about use probabilistic power flow, but you never mention fuzzy power flow. Did you think it was not interesting, or there is another reason, or you just don't care about fuzzy power flow?
No, I mean, it's obvious that I cannot do everything at the same time, and I do not have, let's say, expertise working with fuzzy logic programming. Perhaps it could offer a new solution. Perhaps it could offer another way of doing it. I don't know. I'll need to look into it. But yeah, it was not covered. Let's say that's true.
Okay, I'm satisfied. Congratulations, Mohammed, again.
Thank you so much.
Your thesis.
I just want to answer regarding the buzzwords and the future scenarios. I met you 6 months ago when we were talking about COVID, and I told you we could not have planned for this. And you told me, no, we could have, but when we could have, we didn't. So I think actually thinking about these crazy scenarios is sometimes necessary, because we never know when something might happen. Blockchain or bit or virtual currencies, if someone talked about them 15 years ago, they would probably say he's crazy. But the reason that it was adopted was that a financial crisis happened. People did not sit together and think, okay, let's build this. No, there was a need for it. And then in a crisis, people resorted to things that may not really be the optimal technical solution. But it is the people's response to a crisis. And I think that we might be facing something similar with the energy crisis that we're having now. But anyway, this is a more of a philosophical discussion. I just want
Yes, otherwise we will be talking about and so on.
Yeah. So it's really interesting to stay here for a long time discussing, but you have to understand we need to keep the time. So I think that before passing to the supervisor, I would like just to say a few words, and then we will conclude. So Mohammed, well, congratulations, you did a great job. In fact, as Professor Manomat just said, you have here several theses inside, and from all these contributions that you are providing, would you be able to rank them and to say, okay, well, there is one or two that are perhaps more important than the others? Are you capable to tell me that?
Ranking in terms of the urgency or in terms of the novelty or the potential, let's say, because that's different.
In terms of the potential.
I would rank the last chapter as the most important, and then followed by the one before it. So in other sectors other than the residential sector, because there is a big bias in the research field towards residential prosumers, towards residential applications. There is a very clear bias. And there's very little work done, and there's a huge lag in terms of the transfer of knowledge. So if I would continue working on this thesis, and I intend on doing it, I would start with those, because that's what's lacking.
So that's what you think it's really what is perhaps more relevant and that opens new avenues in terms of further research?
They are all relevant, but in terms of urgency or potential, I would say yes. Yes, I would say that.
Okay, let me just tell you that I still remember you in the several years ago, 4 or 5 years ago, something like that, when you were starting attending my lectures.
The courses. You were my first professor in the doctoral program.
Yeah, I remember that. And I remember you were eager to learn about and to find out a way to proceed. I still remember that. So, well, let me tell you, congratulations once more. You did a good job. And I would like now to pass the word to Professor João Catalão, that of course is the supervisor, because the other supervisors cannot be here. Just for the other members of the jury that are not aware of the policy of the University of Porto. So although you have more than one supervisor, you have 3 supervisors, but the other supervisors, they cannot be in the jury because we don't want to bias the decision.
Yes, only the main supervisor.
There's only one supervisor, the main supervisor.
But it's not the University of Porto, it's the law in Portugal.
Okay, the law in Portugal, thank you. So, and I would like to pass the word to Professor João Catalão and ask him to conclude.
Thank you very much. So first, thank you to Professor Pesser Lopes, our president, and also thank you to all the committee members for your time and availability, especially the ones outside Portugal, let's say the main examiners. But in the end, thank you very much to all of you. This is definitely an outstanding committee. Just a few words about Mohammed Lotfi. So my comments, I'll try to make it in 1 or 2 minutes. My comments are divided in 2 parts. The first part, I call it congratulations. The second part, I call it thank you. So the congratulations are given to the researcher or to the student. let's say, for the excellent work that Mohammed has carried out, dealing, as was mentioned, with many things at once. He tried to handle the residential sector, the transport sector, the industry sector. I think this is a little bit like me. We are, Mohammed is with a background in mechatronics. My background is electromechanics. So we had, our background was to deal with many things at once. So that's what we tried to do when it's called multiple thesis. So he was always a very active, very quick learner, and he had the passion to pursue completely new, creative, even in some cases radical ideas. So he provided really a lot of work during his PhD in very complex topics, multidisciplinary topics, always seeking the highest quality possible. And now the thank you goes to the person, to the individuals for, let's say, the amazing person that Mohammed is. He's always willing to help his friends and colleagues. He was always volunteering to do, let's say, side tasks beyond the PhD itself, for the projects, organization of conferences, of tests, etc. And on a more personal level, he faced COVID alone when he was in Canada. It was an extremely difficult time for him there. So we were mentioning by Professor Marcelino 4 years, actually it was 3+1, because he had 1 year which we also faced COVID, but during the pandemic, he was alone in Canada in the winter. So he was isolated and unable to return to Portugal. It was extremely complicated, and it was very tough for Mohammed, both mentally and physically. Still, he managed to find the strength among himself, in his heart, to do the needful, because he's a resourceful person, a creative person, a determined person, and above all, a sincere person. I think he always had this strength and stamina to overcome all adversities. He's a rare thing about Lotfi is his candor, his honesty, which is very much appreciated nowadays. So in conclusion, congratulations for our research and student. Thank you for our amazing person, individual Mohammed, and I would like to wish him all the best for his future activities. My recommendation, he knows this word, I will tell him one last time, focus, Mohammed, this is the key. Stay focused, this is my recommendation for the future. And if you stay focused, you will be unstoppable. I can be certain that Mohammed was one of the best PhD students that ever worked with me. It was my great pleasure, my great honor to have shared these last 4 years with Mohammed. Thank you very much, Professor Pessalop. This concludes my intervention.
Okay, thank you, João. Thank you very much. So now the jury is going to meet and to deliberate. And so I would like to ask to our services to close the live streaming, and also to ask Mohammed to
exit.
And we will ask you to